Today we're going to talk more about rotations. First, I'd like you to watch the video that's on page 162. Press pause on your video, and when you're ready to move on, press play again. So, exercise 244 is a proof, and we are asked to prove the claim that was made in the video. So, I'd like you to try to complete this proof of that claim in the virtual classroom that for all points P of the plane pi, there exist lines K and L in pi such that P is an element of K and P is an element of L, K is not equal to L, and K is not perpendicular to L. So you can see over on the right, I've drawn a picture. I have a point P in a plane, and P is in this line K, and it's also in the line L, and I've drawn it so that these lines are not perpendicular. So we're just looking to prove that if I have a point, I can draw two lines through that point such that the lines are not perpendicular. Press pause on your video, and when you're ready to check your answer, press play again. So here's my proof. And again, all we're trying to show is that if I have a point, then I can make two lines intersect it and they're not perpendicular. So let's start here. Let pi be a plane and let P be a point in pi. By I3, we know that there exists x and y in pi such that P, x, y are distinct and not collinear. What does I3 say? It says every plane contains at least three non-collinear points. So I know that I have to have three non-collinear points in there somewhere. So I'm going to name them P, X, and Y. They're distinct and not collinear. Then Px is not equal to Py, for if they were equal, then Px and Y would be collinear. In addition, P is an element of Px, the line Px, and P is an element of the line Py. If line Px is not perpendicular to line Py, then we're done. And we can let K equal Px, the line Px, and L equal the line Py. But we also have to show that that's the case if I have chosen three non-collinear points in a plane such that these lines then are perpendicular. So we're going to move on. So suppose that Px and Py are perpendicular, and you can see that I drew myself a picture down here where that was the case. Since x is not equal to y, we know from exercise 134 that segment xy has a unique midpoint that is between x and y and therefore distinct from x and y. So I have drawn a segment xy, and then I drew the midpoint M. Let M be that midpoint. Suppose that M is equal to P. Okay, well that would mean M is over here. Then Px and Y would be collinear, contradicting 1. In 1, we said they were not collinear. So M must not be equal to P, and then we can let our line K equal the line Px. I've named it K here. And the line L be equal to the line PM. I named that here. Remember, we're trying to produce lines that both go through P and are not perpendicular. Suppose that K is equal to L. Then P, X, and M are collinear. So P would be an element of XM here, but XM and Y are collinear. So Y is an element of the line XM. It follows that P, X, and Y are collinear, contradicting 1. Consequently, we know we have now produced two lines that are not equal, K and also L. We have only to establish that K is not perpendicular to L. Suppose, on the contrary, that K is perpendicular to L, so we're going to go at this by finding a contradiction. Then we have two lines, PY here, and PM, PY here, and PM here, that are perpendicular to PX here and pass through the point P. Hence, by P, we must conclude that they are the same line. That is, PY must be equal to PM, because remember, there is only one line perpendicular to another through a given point. But then PY and M are collinear. An argument like the one in the previous paragraph, switching X and Y, reveals a contradiction, so we now can conclude that K is not perpendicular to L, and we're done. Why is exercise 244 important? Well, it's going to ensure that we can always find lines whose composite reflections create a desired rotation. Here's some notation for you. ROT of pi is the set of all rotations on plane pi, and HT of pi is the set of all half turns on plane pi. Give exercise 245 a try. Press pause on your video. When you're ready for the answer, press play again. So this asks the question, if we know that F is a rotation that's not a half turn, and F of P is equal to Q, is that enough information to find F of X for each point X in the plane? And the answer to that question is no. I've drawn a couple points here just to illustrate. So I know that P is going to rotate to F of P. The problem here is that I don't know where the center of my circle is, so I have no way of knowing where any other point would go. So that is not enough information. This begs the question, how much information is needed to determine a non-involuntary rotation? In other words, a rotation that is not a half turn. So we're going to consider a rotation F, where F of P is equal to Q and F of R is equal to S. And we're going to ask, is this enough? Well, there are 4 cases that we need to consider. Our first case is when P is equal to Q and R is equal to S. Okay, well that means that P rotates to Q and R rotates to S. But this isn't possible because rotations have only one fixed point, and that fixed point is the center. So case 1 can't possibly happen. The second case is if P is equal to Q and R is not equal to S. Well, if P is equal to Q, then P/Q must be the center since it is fixed. Then the rotation is determined by the movement of R to S. So let's just take a look. If I know that P is equal to Q there, and R is going to move to S here. Yeah, that's enough. But the way I drew it, I don't really like that because I would need to make sure that S is the same distance from the center. So that would tell me the angle of rotation. It would tell me the orientation of how my points are moving. So I would know in this particular case, the way I drew it, that my circular orientation is negative. It is clockwise. And I would know the angle of rotation. So yes, that's enough. The third case to consider is if P is not equal to Q and R is equal to S. Well, if R is equal to S, that must be the center since it's fixed. Then the rotation is determined by the movement of P to Q. So that is enough as well, using the same argument that I did in the last case. Our fourth case is where P is not equal to Q and R is not equal to S. And I've drawn a picture for you off over here. P is not equal to Q, R is not equal to S. Then the center of the rotation must lie both on the perpendicular bisector of PQ and on the perpendicular bisector of RS. this gives rise to 3 subcases. So let's just think for a second why that is. In order to have a center of rotation, I need this center to be the same distance from R as it is from S, because the image is the same distance as the pre-image. So every point on this perpendicular bisector, and I should mark it like that, is the same distance away from both of those endpoints. So same situation over here. I need the distance from P to the center to be the same as the distance from Q to the center. So therefore, the center must lie in the perpendicular bisector of PQ. And I will just mark it that way. So that is the perpendicular bisector there. So again, this gives rise to 3 subcases. So let's look at the first one. The perpendicular bisectors intersect in a single point C, just like what I've drawn here. Then C must be the center of rotation, which is determined by the fact that it maps P to Q. So once I know the center of rotation, now I can tell everything else about the points in the plane. I know the orientation at which it's rotating, and I also know the angle at which it's rotating. So looking still at case 4, there is another subcase, and in this subcase, the perpendicular bisectors are the same line. So you can see in this picture, I have P and Q, S and R, and I've drawn this perpendicular bisector, and it is the same line. Then the center of rotation is the point in which PR meets QS. You will prove this in the next exercise. The rotation is then determined by the fact that it maps P to Q. Continuing on with case 4, the third subcase says the perpendicular bisectors have no points in common. Then there is no point that could possibly be the center of rotation. In this case, is impossible, and I've drawn a picture over here. There is no way that I can have the same rotation map P to Q and R to S. Next, I'd like you to copy this property in your notes. It says a non-involuntary rotation of a plane pi is determined by its action on 2 distinct points. So in other words, in order to determine a rotation uniquely, a non-involuntary rotation uniquely, you need to know where 2 distinct points move in the plane. Here's the notation for a non-involuntary rotation. In other words, a rotation that is not a half turn. So first we use the symbol rho. This is the Greek symbol rho. It kind of looks like a P. And then a subscript. C is the center of the rotation. So we're going to name the center of rotation. T is the angle measure at which it's rotating. And this is the circular orientation. Now I would like you to try exercise 247. And in that exercise, it asks you to draw the rotation rho sub c, 110 degrees, in a negative circular orientation. Press pause on your video, and when you're ready for the answer, press play again. This is the answer. You were given some directions. Part A said by placing a point X such that X is not equal to C, determine the line K equals the line CX. So you can put that point anywhere and draw the line K so that it intersects X and intersects C. Next, then use the protractor and a straight edge to choose a second point Y to determine the line L equal to CY, so that rho sub C 110 degrees negative equals the composite R sub L circle R sub K. Well, what you need to do in this case is draw it so that the angle between lines K and lines Y is half of 110 degrees. So I want this angle here to be 55 degrees. And I also want it so that it rotates in a clockwise fashion because I'm looking for a negative orientation. So that means I have to draw my 55-degree angle going in the clockwise direction from line K through C. So this is 55 degrees. Then I have my line CY, and then my figure can reflect here and reflect there, and that is the 100-degree rotation with center C and a negative circular orientation. That concludes my lesson for the day. I'd like you to do exercises 246 and 248 through 252. This is also posted in Schoology. Have a great day.